Back in the day, if you wanted to train a neural network to classify any image, you would have to flatten it into a list of pixel values and then pass it through a feed-forward neural network. The problem with this approach is that by flattening the image, we are discarding the essential 2D spatial information that's contained in it. In 1989, Jan LeCun and his team introduced convolutional neural networks, the backbone of many computer vision research for the better part of the past 15 years. CNNs preserve the 2D nature of images and are capable of processing information spatially. In this video, we're going to go through the history of CNNs specifically for image classification tasks, starting from those early research years to the golden era of the mid-2010s when many of the most genius deep learning architectures ever were conceived, and finally discuss the latest trends in CNN research now as they are competing with attention and vision transformers. If you are a student or you're new to this field, this walk down the history books will be an excellent way for you to learn all the major concepts and ideas and seminal papers in this field. And if you're a veteran, then this should be a pleasant nostalgic trip down memory lane. Either way, I hope you enjoy this video. Welcome to Neural Breakdown. Let's set the calendar way back to 1989 where our story begins. At the heart of a CNN is the convolution operation. Let's say we have a 5x5 image of this alphabet C and this 3x3 filter. First, let's pad this image by 2 pixels to make it into a 7x7 image. To do convolution, we will scan the filter across the image and calculate the dot product of the filter with the image at each overlapping location. And this resulting output is called a feature map, and it captures how much and where the filter pattern is present in the input image. In areas of no overlap, the feature map is 0, and in the areas of high overlap, the feature map is at the maximum. In a convolution layer, instead of just one filter, we train multiple filters that all extract different feature maps from the input image. Maybe one is capturing corners and another one is capturing straight lines. And when we stack multiple convolution layers in sequence, we get a convolutional neural net. Let's say you have a feature map with 3 channels and you want to train a layer to transform that into an output of 4 channels. To do this, we train a CNN layer with 12 kernels, 3 for each input and 4 for each output. Each set of input kernels convolve over their respective input channels to output brand new feature maps, and we got these 4x3 matrix of feature maps. Column 1 captures the different spatial properties from the first channel only, column 2 from the second channel, and so on. Finally, we will add all of these feature maps along the output axis, combining different projections of the input channels into a consolidated set of feature maps. And the main takeaway is that each convolution layer simultaneously does 2 things. 1, it runs spatial filtering with convolution. And 2, it combines the multiple input channels together and transforms it into a new set of channels. 90% of the research in the CNNs have been to modify these 2 techniques to improve the performance of these models. The 1989 paper in particular taught us how to train nonlinear CNNs from scratch using backpropagation. They input 16x16 grayscale images of handwritten digits passed through 2 convolution layers with 12 filters of size 5x5, and the filters also move with a stride of 2 during scanning. Strided convolutions are useful for downsampling the input image. After the layers, the output maps are flattened and passed through 2 fully connected neural networks to finally output the probabilities for the 10 digits. Using the softmax cross-entropy loss, the network is then optimized to predict the correct labels for the handwritten digits. After each layer, the tanh nonlinearity is also used, allowing the learned feature maps to be more complex and expressive because of the nonlinearity. To understand exactly why CNNs are so powerful, we have to understand the concept of inductive bias. Inductive bias is a concept in machine learning where we deliberately introduce specific rules and limitations into the learning process to move our models from general solutions and steer it more towards solutions that follow human-like understanding. When humans classify images, we also do spatial filtering to look for common patterns across the image and then form multiple representations that we finally combine to classify an apple or a table or a chair. The CNN architecture is designed to replicate just that. In feed-forward networks, because we are flattening the image, each pixel is treated like its own isolated feature, just independent and equally important as all pixels. In CNNs, there is more parameter sharing because the same filter scans the entire image. Inductive biases make CNNs less data hungry too because they get local pattern recognition for free due to the network's design, whereas feed-forward networks need to spend their training cycles learning about that behavior from scratch. In 1998, Jan LeCun and his team published the LeNet 5 model, a deeper and larger 7-layer convolutional neural network. They also used max pooling, which, like strided convolution, also downsamples the image by grabbing the maximum values from a 2x2 sliding window. Also notice that if you train just one 3x3 convolution layer, each neuron in the feature map is connected to just a 3x3 region of the original input image. This is called the neuron's local receptive field, the region of the image where this neuron is extracting all of the patterns from. But when we pass this feature map through another 3x3 layer, the new feature map indirectly creates a receptive field of a larger 5x5 region from the original image. Additionally, when we downsample the image through max pooling or strided convolution, the receptive field also increases, making deeper layers be able to access more of the global properties of the image. For this reason, earlier layers in the CNNs only learn low-level details like specific edges and corners, but later layers pick up more widespread global-level patterns. As impressive as LeNet 5 was, researchers in the early 2000s still deemed neural networks to be computationally very expensive and data-hungry to train. And there were also problems with overfitting, where a complex neural network will just memorize the entire training dataset and just fail to generalize on new unseen data. The researchers instead focused on traditional machine learning algorithms like support vector machines that were showing much better performance on the smaller datasets that were available at that time and the low computational demands that it posed. But believe it or not, the next massive impact after LeNet 5 came all the way in 2012. And that was caused by the availability of the ImageNet dataset, which was open sourced in 2009. It contained 3.2 million annotated images covering over 1,000 different classes. Every year from 2010 to 2017, we got this massive competition called the ILSVRC, where different research groups will publish models to beat the benchmarks on a subset of the ImageNet dataset. In 2010 and 2011, traditional machine learning models like support vector machines were winning, but starting from 2012, it was all about CNNs. The metric that was used to rank these different networks was generally the top 5 error rate. The lower the top 5 error rate, the better the model. And in general, the human error rate is known to be around 5%. So anything close to that will be considered human level performance. And if we beat that, it's kind of superhuman level. Spoiler alert, we're going to get there. These models are going to get so crazy and powerful that the ImageNet competition will be considered solved by 2017. And that revolution started all the way in 2012 when AlexNet was introduced by Dr. Jeffrey Hinton with a top 5 test set error of 17%. And by the way, if you're enjoying this video, all you need to do to support the channel is to simply hit that like button right now and subscribe to the channel. Literally, that's all you need to do. And that'll make all the effort of putting this video together worth it. You can also become a member of the channel or support us on Patreon, which not only helps the channel to grow, but you'll also receive some nice perks like access to all of the slides, write-ups, annotated PDFs, animations from this video, and all the other videos in the channel. So do it, and let's get back to the video. Here are the 3 main contributions from AlexNet. AlexNet trained on 224 by 224 RGB images and also used multiple kernel sizes in the network, 11 by 11, a 5 by 5, and a 3 by 3 kernel. Models like LeNet 5 only use 5 by 5 kernels. The larger kernels were more computationally expensive to train because they just contain more weights, but they also capture more global widespread patterns from the images. Because of these large kernels, AlexNet had over 60 million trainable parameters. But all that complexity can lead to overfitting again. And to alleviate that, AlexNet used a regularization technique called dropout that Hinton's team introduced earlier in the same year. Basically, during training, a fraction of the neurons in the network is turned to 0. This prevents the network from being overly reliant on specific neurons or groups of neurons for generating a prediction, and instead encourages all of the neurons to learn general meaningful features which might be useful for classification. AlexNet also replaced the tanh nonlinearity with ReLU. ReLU is an activation function that turns negative values to 0 and keeps positive values as is. The tanh function tends to saturate for deep networks because the gradients get really low when the value of x goes too high or too low, making optimization really slow. ReLU instead offers steady gradient signals to train the network, seemingly about 6 times faster than tanh. And here are some highlights from the AlexNet paper. In 2014, the GoogLeNet paper got the ImageNet top 5 error rate of 6.67%. The core component of the GoogLeNet was the Inception module. Each Inception module consists of parallel convolution layers with different filter sizes, 1x1, 3x3, and 5x5, and also contains max pooling layers. Inception applies these kernels to the same input parallelly and then concats them, combining low-level and medium-level features together. 1x1 kernel just multiplies each pixel with a fixed value, which is why they're also called pointwise convolution. And each 1x1 kernel only contains a single value, which is multiplied to the entire input channel. So the resulting feature maps are just scaled version of the input. The first column just contains scaled versions of the first channel, the second column of the second channel, and so on. And finally, these columns are added, effectively combining the different projections of the input channels and mixing them together to go from the 4-channel input to a 3-channel output. Also notice that a larger kernel like a 3x3 kernel does the channel mixing too, but it also does spatial filtering. 1x1 kernels do not do spatial filtering. It only does channel mixing, and it does so very efficiently with a low number of weights. A 3x4 grid of 1x1 convolution layers train only 12 weights, but if there were 3x3 kernels, we would be training 108 weights. The reason why GoogLeNet uses 1x1 conv layers is to do dimensionality reduction, which is to reduce the number of channels before they run spatial filtering with the 3x3 and 5x5 convolution layers. This helps to cut down on the number of trainable weights in the network even more. And this network pattern will come up a lot in CNN research. Use 1x1 convolution to quickly decrease the number of channels from a high number to a lower number. Then use spatial filtering with 3x3 and 5x5 kernels, and then use another 1x1 convolution layer to expand the number of channels back. And here are some highlights from the GoogLeNet paper. The VGT network makes this interesting claim that we do not need larger kernels like 5x5 or 7x7 at all, and all we need are 3x3 kernels. A 2-layer 3x3 convolution network has the same receptive field that a single 5x5 layer does. 3x3 layers have the same as one single 7x7, but it also does so with fewer parameters. One 5x5 filter strain 25 weights, right? But two 3x3 filters strain 18 weights. Similarly, one 7x7 trains 49 weights, while three 3x3 trains 27. Training with deep 3x3 convolution layers became the standard for a long time in CNN architectures because of the VGT network. So deep neural networks can suffer from a problem known as internal covariate shift during training. Since the earlier layers of the networks are constantly training, the latter layer needs to continuously adapt to the constantly shifting input distribution that it receives from those previous layers. Batch normalization aims to counteract this problem by normalizing the inputs of each layers to have zero mean and unit standard deviation during training. Batch norm also allows the network to converge around 14 times faster because of this, and lets us use higher learning rates, and also makes the network robust to the randomly initialized weights at the start of training. So imagine you have a shallow neural network that has great accuracy on some classification task. Researchers found that if we added, say, 100 new layers on top of this small network, the training accuracy of the model could actually go down. This is really counterintuitive because all these new layers need to do is just copy the output of the shallow network at each layer and at least be able to match the original accuracy. However, really deep networks are notoriously difficult to train because gradients can saturate or become unstable when backpropagating through many layers. The good folks at Microsoft introduced ResNets in 2015, and that allowed us to stably train 150-layered CNNs. What did they do? The core idea of ResNets is residual learning. The input passes through one or more CNN layers as usual, but in the end, the original input is added back to the final output. These blocks are called residual blocks because they don't need to actually learn the final output feature maps in the traditional sense, but instead they just need to learn the residual features that must be added to the input to get the final feature map. If the weights in the middle layer were to just turn themselves to 0, then the residual block will just return the identity function, meaning it will be able to easily copy the input x. Genius. During backpropagation too, the gradients can directly flow through these shortcut paths to reach the earlier layers of the model really fast without much vanishing. And that's why ResNet can stack many of these blocks together to form really deep networks without any loss of accuracy. And with this remarkable improvement, ResNet managed to train a 152-layer model that got a top 5 error rate that just shattered all previous records. And here are some highlights from ResNets. DenseNets also add shortcut paths connecting earlier layers with later layers in the network. A DenseNet block trains a series of convolution layers, and the output of each layer is concatenated with the feature maps of all the previous layers in the block. Each layer basically adds a small number of new feature maps to the collective knowledge of the network as the image flows through it. DenseNets have an improved flow of information and gradients throughout the network because each layer has direct access to the gradients from the loss function at the final layer. And here are some highlights from DenseNets. As we discussed in the first section of the video, convolution layers do two things: filtering spatial information and combining them channel-wise. And the MobileNet paper separates these two operations into their own individual layers. Given an input set of feature maps with M channels, first they use depth-wise convolution layers that train M 3x3 convolution kernels. Unlike normal convolution layers that perform convolution on all feature maps, depth-wise convolution layers perform convolution on just one feature map each. Second, they use one-by-one point-wise convolution filters to mix all these feature maps together. And by separating the filtering and combining steps like this, it drastically reduces the number of weights, making it super lightweight and still retain a lot of the performance. And here are some highlights from MobileNet. MobileNet V2 improved on the MobileNet architecture by introducing two more innovations: linear bottlenecks and inverted residuals. MobileNet V2 uses one-by-one point-wise convolutions to first do dimensionality reduction across the channels. Depth-wise convolution layers then are used for spatial filtering, and another one-by-one point-wise convolution layer is used to expand the channels back. These bottlenecks don't pass through ReLU and are instead kept linear, and that's why it's called linear bottlenecks. If you use ReLU, it will zero out all of the negative values that come out of the dimensionality reduction step, and this can cause the network to lose valuable information, especially if a bulk of that lower dimensional subspace was negative. The second innovation is called inverted residuals. Generally, the residual connections occur between layers with the highest number of channels, because intuitively that's where the maximum information lies, right? No. According to the authors, the main information is actually captured inside the bottleneck layers. They compress all of the information from those high channel layers into a lower dimensional subspace. And that's why the authors actually add shortcuts between these bottleneck layers. And here are some highlights from MobileNet V2. And while all of these epic computer vision research was going on, there is a different storm brewing in the natural language processing research. Transformers and attention mechanisms provide a highly parallelizable, scalable, and general architecture for modeling sequences. Many papers had tried to incorporate attention into the vision landscape as well. For example, the Squeeze and Excitation Network, or SENNet, applied a self-attention-like method to make each channel of a feature map contextually aware about the global properties of all of the other input channels. However, the paper that we're going to cover in this video are vision transformers, or VITs, that established that transformers can indeed beat state-of-the-art CNN models in image classification. The input image is first divided into a sequence of fixed-size non-overlapping patches. Each patch is independently embedded into a fixed-size vector, either through a CNN or passing it through a linear layer. These patch embeddings are added with their positional encodings and are inputted as a sequence of tokens into a self-attention-based transformer encoder. Self-attention models the relationship between every patch with respect to all other patches and outputs new, updated patch embeddings that are contextually aware of the entire image. Where CNNs introduce several inductive bias about images, transformers do the opposite. No localizations, no sliding kernels, and they rely on generality and raw compute to model the relationships between all of the patches of the image, irrespective of how far they are spatially. Inductive biases are great on smaller datasets, but the promise of transformers is that when we have massive training datasets, a general framework is going to eventually beat out the inductive biases offered by CNNs. And maybe in a future video, we are going to discuss all about transformers for computer vision. So make sure you are subscribed to get notified. But this is a CNN video, so we are going to end with a CNN paper. ConvNext, a ConvNet for the 2020s. This paper creates a convolution-based no-attention network that managed to outperform all of the transformer-based models. And there is no major innovation here, but instead it's a very deep comparison of what makes CNNs and transformers different, and then create a ConvNet that retains the best of both worlds. Here are some of the main points from this paper. The input of ConvNext follows the patching strategy in vision transformers. A 4x4 convolution kernel is trained with a stride of 4, which is used to create a downsampled images similar to the patch embeddings in the original VIT. Inspired by MobileNet, ConvNext uses depth-wise separable convolution layers. The authors also hypothesize how depth-wise convolution is kind of similar to the weighted sum operation in self-attention, which also operates on a per-channel basis by only mixing information in the spatial dimension. ConvNext uses large 7x7 filters to capture a wider spatial context, trying to come close to the fully global context that VITs capture while still retaining the localization spirits of CNNs. And there are also some other tweaks like using the MobileNet V2 inspired inverted bottlenecks and replacing ReLU with GeLU activations, layer norms instead of batch norms, and more that shapes up the rest of the ConvNext architecture. ConvNext are more computationally efficient because of their depth-wise separable convolution functions, and more scalable than transformers when it comes to high-resolution images, because self-attention scales quadratically with the sequence length and convolution doesn't. The future seems super interesting for what is to come with computer vision research. The rich history of steady architectural improvements in CNNs have taught us much about deep learning, inductive bias, and most generally, computation itself. With all the major advancements from the brilliant short and sweet papers from the 90s to the roaring highs of the 2010s with AlexNet, VGG, GoogLeNet, DenseNet, MobileNet, all of those models, and finally the new era where transformers and CNNs will compete and prove which ideology is superior, inductive bias or generality. Do drop a like and please drop a comment. Anything would do because it helps promoting this video. Check out our membership options, and speaking of which, a huge thank you to all of the members who have supported the channel this month. Thank you, you are magnificent.